Welcome again to Let's Talk Advanced Chemistry, Chemistry 2 with Pastor Dan. We're looking over here at acid-base reactions, and this entire section is going to be a review from last year. So you can either watch this one, but then go back if you need more, look into Chem 1 when we talked about acid-base chemistry. A lot of the definitions and the first concept of pH expressed here. So we looked at acid-base chemistry. The first definitions of acid bases were brought forth by Arrhenius. Remember, Arrhenius is the one we just talked about not too long ago, dealing with the kinetics to find the energy of activation. So according to Arrhenius, a acid is a substance that produces hydrogen ion when it dissociates. Remember, dissociate means breaking apart into its base ions. A base is a substance that produces hydroxide. Now, there are substances like ammonia and calcium carbide. Both of those are basic. And calcium carbonate. Both of those are basic and they don't have hydroxide. So two different scientists working at the same time came up with the answer at the same time, how to rename those. And so we give them credit. The first is named Bronsted, the second is Lowry. If we look at hydrogen ion, remember, hydrogen ion is a proton without the electron. So all it is a proton. So both Bronsted and Lowry identified that an acid is a proton donor. So they're giving up protons. And then if an acid donates, that means the base has to accept a proton. So two different ways to define these again. Produces hydrogen ion in dissociation, that's an acid. Produces hydroxide ion, that's a base, according to Arrhenius. According to Bronsted Lowry, a proton donor is an acid and a proton acceptor is a base. All right, now I want to talk about a couple of definitions here before we get too far. Conjugate acid, conjugate bases. Conjugate acid substance acid in the reverse reaction. Conjugate base acts in the reverse reaction. Now this involved processes of equilibrium when it's coming back. Okay, let's show a quick reaction. Very simple first, the best one to do. Hydrochloric acid with sodium hydroxide. When we do that, we generate sodium chloride plus water. My acid, starts with an H over here, so this is my acid. Hydroxide, this is my base. NaCl is called my salt. Now, by definition, a salt is any ionic compound that is not an acid or base. So if you have a substance that's not acidic or basic in nature and is ionic, we call that a salt, and the other product is water. Any reaction of an acid and base is always going to generate a salt and water. Now, how do we know if we have equilibrium? Well, we have equilibrium when we talk about weak acids and weak bases. How do we identify them? Now, these are generalizations. They're not always true, but it just makes it easier for beginning students to get a solid. All right, so if it's binary, if it's like H with one other ion, H2S, HCl, HBr, HF, HI, all of those we consider strong. So like HCl. If it's a polyatomic, now that what means strong, it dissociates 100%. It goes completely to its ions. We have no equilibrium going on. For polyatomic ions, we take the number of oxygens in it, subtract the number of hydrogens. If that number is greater or equal to 2, we consider that a strong acid. All right? Transversely, if the number is less than 2, it's a weak. Now, what do we do about bases? Well, if it has hydroxide, consider it strong. Doesn't have hydroxide, it's weak. Real simple, keep it easy. At this point, there's actually a value called Ka and Kb that we can look at to help us get an understanding of that. We'll do that in a little bit here. Right now, conjugate acids and bases. Quick review again. Here we're looking at this process. So acid is, because it starts with H, my hydroxide is my base. Now, how do we know? Remember, 2 minus 1, that's 1. So this is weak, and this is going to be strong. If one or both are weak, then it's equilibrium. So when you do the double replacement, we're going to put barium with nitrate oxidation numbers plus 2 minus 1. So Ba parentheses NaO2 parentheses twice, plus water is the second product, HOH, hydrogen hydroxide, that's water. Balanced, that's my salt. Now, we don't have to always identify water, but that's a good thing to do, which is going to be my conjugate. Remember, so a conjugate substance acts in the acid in the reverse reaction. Base acts. So in this one, which one has hydrogen out front? Well, that'd be water. 99.9% water is my conjugate acid, and my salt is my conjugate base. Let's do another one. Let's do sodium carbonate plus hydrofluoric acid. Again, my acid, my base and my acid. We identify the acid because it starts with the H, and the other one has to be the base. And this carbonates often make bases. This is going to be weak because it doesn't have hydroxide, and that's strong. If one or both, it's going to be equilibrium. Put sodium with fluoride, NaF, +1 -1. H with CO3, +1 -2, so it's H2CO3. Wait a minute, you said that'd be water in there. Well, there is. See, carbonic acid is carbonated water. So once we get carbonic acid, we spontaneously break it into water and carbon dioxide. All right, so what's my salt there? My water. Which one's my conjugate acid? Still water. My conjugate base. Good. All right, here's to try these, pause them, work them through, see what we get. Ready? Any questions? ltslpd@gmail.com. Remember, like, subscribe, share. All right. The first one's a direct reaction, LII plus H2O. There's no conjugates. We're not coming back. Second one does have conjugates. We're for carbonic acid again. All right. Let's move forward now. Try this. Again, that's probably good to see if we can get some word association. Remember, hydroic acids are ides, ic acids are eights, and ate acids are us's. So in case you forget, that's the reactants for the first one, reactants for the second one. Pause the video, finish these up. Here we go. All right. Now, one last process we're going to look at then, and that has to do with pH. Now, when we do pH, we're going to do a value called Kw. The Kw value is 1 times 10 to the -14th. Very, very small number. It's a dissociation of water. We don't have water underneath it because of the fact that water is a liquid and we don't have concentrations. Now, we want to make this easier. So what we're going to do is we take the negative log of both sides. Negative log of it's going to make it a number that we can use called 14 is equal to pH plus POH. Now, from that, we get a couple values that we can work with. pH is a measure of acidity. POH is a measure of alkalinity. How much of an acid, how much of a base. All right, so additional equations we should use for these. We talked about this last year. pH is equal to negative log of hydrogen ion concentration. POH is negative log of hydroxide ion concentration. Hydrogen ion is 10 to the minus pH, and hydroxide ion is 10 to the minus POH. Again, we talked about this last year, so go back and look. So these 5 equations right here is what we need to solve for pH. We're going to do 2 of these. So let's do the first one. Determine the pH, the POH, hydrogen ion, and hydroxide ion for 0.8995 molar hydrosulfuric acid. So the first thing you do is identify the acid, H2S. It's a strong acid. I'm only going to do a strong acid for the pHs for right now. So it means it's going to dissociate 100% into 2H and S2 minus. Okay, so hydrogen ion. Well, we know from the equation that it's 1 to 2. So to find the hydrogen ion concentration, it's going to be twice the acid concentration. So from the problem we see, that's 0.8995. So 2 times 0.8995, we're going to get 1.9799 molar. That's a hydrogen ion concentration. Hydrogen ion is gone. Now, what are we going to find next? Well, we know hydrogen ion, we find pH. pH is negative log of hydrogen ion. So plug in the equation, negative log 1.766. You can get a negative. That's 99, sorry. pH usually goes from 0 to 14. You can get negative. That means it's very strong. You can go above 14. It's very basic. All right. And then define pH is gone. Define POH. pH plus POH is 14. So we're going to solve POH. We're going to move. This caused me a little confusion. What I did here is I just plugged that in there. We're going to add that across to solve pH. We're going to add 0.02550 to both sides. When we do, the other side, and we're going to get POH is equal to 14.255. Oh, last field column. All right. And then lastly, define hydroxide ion. We said that was 10 to the minus POH, 10 to the minus 14.2550. Put that in the calculator. I have 6 sig figs. Answer is 5.55904 times 10 to the minus 15th molar. All right, great. Let's try one more of these. Those are our answers. Let's try one more of these, okay? So work through this. I'm going to show the steps here. Any questions, let me know. Ready? All right, that's all the work. That's it for today. No problem. Hopefully you got this. Take care. God bless. Bye.